This is a video about the wave equation. We're going to look at waves two different ways. In this version of the wave, it's set up so that horizontally we're measuring the wavelength. In this version of the wave, we're looking at it so that horizontally we are measuring the period. In the vertical, we're still measuring the amplitude. So if we're going to write out an equation and we're going to focus horizontally on the period and not the wavelength, we can write out an equation either this form, a cosine omega t, or a cosine 2 pi ft, where xa omega, that's supposed to say omega, t, f, and capital T represent those things there. It's really important for us to, first of all, look at the graph and realize that horizontally we're looking at time and not distance, because that's what this equation is set up for. Now x, that can be a little confusing. X is how far the wave is displaced from the equilibrium. That means how far above in this case or how far below this zero equilibrium mark. It does not represent anything horizontal because remember, in the horizontal, we're measuring time. So I expect you to be able to do one of two things. I expect you to be able to see the graph or observe the graph and write one of these two equations, or from one of these two equations, sketch this graph. So let's start with just looking at the graph. So just by looking at the graph, if we look from crest to crest, or same part of the wave to the same part of the wave, technically this is not the wavelength. So from here to here, this is the this distance would be the period. So we would take this equation and find the inverse of it to find the frequency. So 1 over 1 is 1. I wish I used different numbers because the inverse of 1 is obviously 1. We would take that value, the period 1, take its inverse, find the frequency of 1, plug it into there for the frequency, and this is the equation we would end up with. We'd put a 1 there. Because the height or the maximum displacement from there to there is the amplitude, we would take the amplitude and put it right there. So that's how we would start with, that's how we would get that equation. Obviously, if we multiply it out, we would get 6.28 t. So working the other way, what we could do is if we've got the this equation, we would realize that the value that comes before the trig function, whether it's sine or cosine, that value there represents the maximum displacement, also called the amplitude. Then from this part here, the number before the t, we would know that that represents 2 pi f. So from that value to or 6.28, we could divide that by 2 pi to get the value 1, and that would give us the frequency. We would take the inverse of the frequency to get 1, and that would be the period. So that's how we would go about getting the period. Now notice this is a cosine graph. We're starting over here at the maximum. If this was a sine graph, we would start right here at 0. Notice everything else is the same except that instead of cosine, we're using sine. So again, I expect you for this kind of graph to also be able to go from the graph and write out one of these two equations, or look at one of these two equations and go to the graph. And if you would like to look at more specifics about this, here's a little, your notes include a more specific explanation if you're curious. One of the things you will notice is this angular speed, and you're probably wondering where that comes from. Well, what happens is the wave can be modeled as this spinning unit circle, as it's called. There's the position where it's moving up and down. This angular speed of this circle is related to this position. And that angular speed corresponds to this omega here, the 6.28 radians per second in this particular example. And that's it.